Problem number 2 from exam 1. A boy standing at the edge of a vertical cliff. Well, this looks familiar. We had a homework problem like this, and there was a problem like this on last year's exam. But this one is tweaked a little bit. In fact, it's simplified to make it a little bit shorter and easier, I hope. But let's start off by making a drawing just to remind myself of what's going on. So you've got a boy standing at the edge of a cliff. There's water down here. Let's just make the cliff height h. And he throws a stone off the cliff, and it has an initial angle of 30 degrees with respect to horizontal. Okay, I'm given I'm not given the velocity that he throws it at, except I'm given the direction of it, so I'm really not given the speed. So the initial velocity is unknown. What we do know is it reaches its maximum height at t equals 1 second, and that it splashes into the water t equals 6 seconds after it's released by the boy. And so the first question that I'm asked is, what is the speed of the rock when the boy threw it? How am I going to do this? Well, because I'm given the time it takes to the maximum height, and if I focus only on the vertical motion, that must tell me the speed, initial component of the velocity in the y direction. You know how far up it goes, you know what it must have been thrown at, or how long it takes to reach its maximum. You know its initial velocity. Okay, so we can solve for v naught y just with this information. Okay, and to do that, you also have to recognize that v naught final, now over this interval, over 1 second, okay, v final in the y direction is 0. V naught in the y direction is what I'm after. The acceleration equals negative g in the y direction over this part of the path. And I can use the idea or the equation that v final y equals v naught y plus the acceleration times the time, which in this case, the v final y is 0. V naught y is v naught over all times sine of 30 degrees. I'm only interested in the vertical component of the motion, minus 9.8 meters per second squared, because that's the acceleration, and the time is 1 second. This I can solve for v naught because I know every other term here. I can rewrite it as v naught equals 9.8 meters per second squared times 1 second divided by sine 30 degrees. Pull out the calculator, and I find this is 19.6 meters per second. So I've solved part A for the speed of the rock when the boy threw it. Okay, question B. How high above the lake is the cliff? Okay, I'll think for a moment. Now I'm after the height of the cliff, h, okay, above the lake. And thinking about it just for a moment, I realize that, hey, my basic equation of motion in the y direction would be y final over any interval equals y naught plus v naught yt plus 1/2 at squared. And I know all these numbers except y final minus y naught, but that's what I'm after. I know the initial velocity in the y direction. We just solved for that basically. I know the overall time is 6 seconds. And I know the acceleration in the y direction is g, down. So this equation should let me solve for it. Applying it in this case, I've got 0 is the final position when it hits the lake equals h plus v naught sine theta, okay, where v naught comes from the equation I just solved. And finally, that's times time minus 1/2 gt squared. Okay, so rewriting this in terms of h, which is what I'm after, I know all the other terms here now. H is equal to 1/2 gt squared minus v naught sine theta times the time. And I could start plugging in numbers. 1/2 times 9.81 meters per second squared. T squared is 6 seconds squared. Okay. Minus v naught, which is 19.6 meters per second. times sine of 30 degrees times the time, which is again 6 seconds. Okay, pull out the calculator, do the math, and I get 118 meters for the height above the cliff. Now part C says how far up from the cliff does the rock land, measured horizontally from the base of the cliff. And this is a straightforward application of, again, an equation like this, the equation of motion, but now in the y direction, in the x direction. So x final equals x naught plus v naught xt plus 1/2 the acceleration in the x direction t squared. And there is no acceleration in the x direction for projectile motion. And there's only acceleration in the y direction. So this is going to be pretty easy. I can define my initial x component, or x position, to be 0. My velocity in the x direction never changes. It's v naught cosine theta times the time. Plug in the values, the numerical values. That's 19.6 meters per second. Cosine 30 degrees times 6 seconds. Pull out the calculator. 102 meters. Done with problem 2, although in truth I actually went back and checked this using some other equations to see if I get the same answer. That's always reassuring when I do, and in fact I did. In fact, what I did is I said, okay, let me solve for the height to the maximum height. And so I found this distance, and I said, well, let's see if I can then find how long it goes from here to there, knowing that the velocity in the y direction is up there. And so I found that separately, and then I did just a little bit of second grade math, addition and subtraction, to see that I got this using completely different method. And it worked. So I'm confident about problem number 2.